In today's video, I want to talk about the circuit that is shown on the screen. This circuit is a R-2R ladder DAC, and I want to just explore how this DAC works. A DAC, of course, is a digital to analog converter. It converts a digital code into an analog value. And in this case, we have a 4-bit digital value. And the reason we know that is because we have 4 switches, each representing a particular bit of the digital code. And let's just call these switches 1, 2, 3, and 4 as I just marked on the screen. And what we'll do is we'll switch on each of these switches at a time and see how the circuit works. Okay, so let's say the digital code that we want to convert into an analog value is 0 0 0 1. So only one of these switches, the switch 4, is on while all the other switches are off. And what does it mean to say that these switches are off? What we mean by saying that these switches are off is that the switches are connected to ground. Okay? And what do we mean when we say that this switch is on? It means that it is connected to VREF. Okay, so now let's look at the output of the signal corresponding to this code 0001. So if you look at the output of the circuit, the way to do it would be to start to analyze this circuit from the left hand side. So this 2R and this 2R are in parallel to each other. So the combination of this circuit would be simply a resistance of value R connected to the ground, and that goes and connects at this point, right? And this R, which is a combination of these two elements, and this R make 2R, which is in parallel with this 2R. So they make a value of R, and then you get R plus R. This R is 2R, which is in parallel with this 2R, so it makes R again. And that R and this R make 2R. So basically, you can reduce the circuit to something like this. So you have a resistance of 2R, which is connected to the ground. And then you have another resistance here, 2R, and that's this resistance, which is connected to VREF. And we are taking the output of the circuit from this point, V out. So what is V out going to be? It's fairly easy to see that this 2R and this 2R are forming a voltage divider circuit. So V out is going to be VREF over 2. Okay, so we have this ladder circuit, and we just looked that for a code of 0001, the output that we get is VREF over 2. Okay, so now let's try another code and see what we get. So let's try a code of 0010. So what we have done is we have turned on the second switch, the third switch, while switching off the fourth switch. So the connection here is to ground. The connection here is to VREF. That's the correct connection. Here it's connected to ground, and here also it's connected to ground. So how does the circuit look now? What would be the output of the circuit? So again, if you look at the circuit till here, if you look at this side of the circuit, what you will find is this resolves into a resistance of 2R that is connected to ground, right? So this 2R and 2R form the value R, the resistance R. This circuit, this resistance added to that R becomes 2R. 2R in parallel with 2R is R. R plus R is 2R. So you could draw this like this. So you have resistance connected to ground, which is 2R, and then you have a resistance connected to VREF, and this resistance value is also 2R. And then instead of the output, as in the previous case, you have an R and a 2R which is connected to ground, and we are taking the output at this point. This is 2R, this is R. Okay, so that's the equivalent circuit that we get. So what is the output of the circuit at this point? Now, of course, what you can do to work out the output is to write some nodal and mesh equations and solve it. But I think there's an easier way to do this, and by using Thevenin equivalence. So what would be the circuit, the Thevenin equivalent of the circuit, if you look to the left of this red line? Now, if you remember how we do our Thevenin equivalence, you would remember that the voltage at this point is your Thevenin voltage, which is V ref over 2, right? If the circuit on the right is not connected, this is going to be V ref over 2. And what is the resistance looking in if we switch off this V ref? That means if for a time being you connect this to ground, what is the resistance here? It's of course R. So we can therefore replace this circuit with its Thevenin equivalent. And how would the Thevenin equivalent look? The Thevenin equivalent would simply be a voltage of V ref over 2, and that is connected through a resistance of R. And then you have this circuit here, right? So you have R here, and then you have 2R here, and you have V out. So what is V out going to be in this case? Now this two resistors add up to 2R, so that's half of V ref over 2. So V out is going to be V ref over 4. So when the code is 0010, the output is V ref over 4. Next, what we'll do is we'll look at another code, and we'll use the value 0100. So what we are doing is we are turning off these switches or connecting them to ground, leaving this on and turning this off as well. And let's look at what output do we get for this circuit. Now, as we looked before, for the circuit that is connected this side, you can just reduce it to a resistance of 2R connected to ground. And then you have 2R with V ref connected here. And then you have R, 2R connected to ground, R, and 2R connected to ground. 2R, R, and that's V out. Now we can replace this part of the circuit with its Thevenin equivalent, and what we get is a voltage of V ref over 2, a resistance of R which is connected in series with R, and then there's a 2R connected to ground, another R, another 2R. So that's, and then you have a V out here. So what we can try to do now is to replace the left hand side of the circuit to this line with its equivalent circuit. And if you follow the methods that we have looked at before, what you should be able to see is you should be able to get a signal of value V ref over 4 instead of 2, and you get a resistance of R, and you have another R, and you have this 2R going to ground, and that's V out. And this, of course, easily leads us to get V out equal to Vref over 8. So the signal here is going to be Vref over 8 for the code 0100. So for a code of 0100, you get Vref over 8, and so on and so forth. So what you would see is for a code of 1000, you will get a signal of Vref over 16. So what's happening is that the signals at each of these points is multiplied by a factor of Vref, either Vref over 2 or Vref over 4 or Vref over 8 or Vref over 16, depending on which position it is. So this bit here, switch 4, is our most significant bit, while this bit here, switch 1, is your least significant bit. And you can see that this circuit acts like a DAC. One of the advantages of using a circuit like this is that you only need two values of resistances instead of the DAC that we were using before, which was binary weighted DAC. So if you compare it to the binary weighted DAC where you need resistors of different values, you would need resistors R over 2, R over 4, R over 8, and so on and so forth. Here you need only two values and you can perform the entire DAC operation, and that makes it much more easier to do it.